Hello class, this is going to be our flipped classroom on bonding part 2, the second in our series of bonding videos. So in this video we're going to focus on covalent bonds or molecular bonds. And the first thing you need to know is that, once again, that the word covalent literally means sharing electrons. So when will we have a covalent bond? It will always be between two nonmetals. So how can I tell if something's going to be ionic rather than covalent? Well, if it's ionic, it's going to be between a metal and a nonmetal. That's always an ionic bond, because if you remember, ionic means transfer of electrons, and when a metal and a nonmetal get together, the metal will lose all of its valence electrons and the nonmetal will gain them. So if you have a metal and a nonmetal, it's ionic, but if you have two or more nonmetals, that is going to be covalent. Now, there is another way to determine whether a bond will be ionic or covalent, and that is by checking the electronegativity difference. Now, this one is not foolproof because there are some exceptions to this, but in general, this works. So here's what I'd like you to look at. I've drawn a number line between the numbers 0 and 4, which is the electronegativities that different atoms can have. If you were to compare two atoms and look at their electronegativities, you will find that if you subtract the difference, and if that difference is 1.7 or higher, then that will make an ionic bond. But if the difference is less than 1.7, that's going to be covalent. So for example, let's say I wanted to know whether the compound NaCl was ionic or covalent. Again, I know Na is a metal and I know Cl is a nonmetal, so clearly it has to be ionic, but let's use that system we just said. I'm going to flip to the reference table and look in the back and see if I can find the electronegativities. So let's see, I got to find Na first, and Na is there. It has an electronegativity of 0.9. Cl is there. It has an electronegativity of 3.2. So therefore, if I do 3.2 minus 0.9, let's see what I get. So 3.2 minus 0.9 would be 2.3. That would be the difference. 2.3 is clearly in this area here, therefore it is definitely ionic. But again, we already knew that, metal and nonmetal. The only reason why I like this little number line is I can compare two ionic compounds and say which one is more ionic. And the one that's more ionic will have a bigger difference in electronegativity. Now let's find one that is covalent. Let's say I'm looking at not NaCl, but HCl. And again, I already know HCl is covalent because it's two nonmetals, but let's confirm it with this little chart here. Hydrogen has an electronegativity of 2.2, and we already know chlorine has an electronegativity of 3.2. So if I compare the difference, 3.2 minus 2.2 is 1.0. That is definitely in the covalent region, so that would be covalent. But again, like I said, I wouldn't generally use this formula if I'm trying to determine the difference between these two. I can always just use the metal nonmetals ionic, nonmetal nonmetals covalent, and that always works. Because like I said, there are some exceptions to this. Now, the next thing I want to talk about are types of covalent compounds. There are different types of covalent. One type is when they share equally. Remember we said covalent is sharing? If the electrons are being shared evenly between the atoms, we call that nonpolar. Why nonpolar? Because nonpolar means no pull of electrons. The electrons are literally being shared 50-50 between the two atoms. So when will a bond be nonpolar? If the two atoms have no difference in electronegativity, or in other words, they have the same electronegativity, then the bond is nonpolar. So for example, there's a molecule called Cl2. It's a diatomic molecule. Remember, diatomic means two of the same. If I were to draw it out, here's how I draw it. Cl has 7 dots, 7 valence electrons. 1, 2, 3, 4, 5, 6, and that one right there is 7. And this Cl also has 7. 1, 2, 3, 4, 5, 6, and 7. So remember, the goal is to have an octet, or 8 electrons. So by sharing these two electrons, each chlorine can say, yep, I now have 8. Here are my 8. 2, 4, 6, 7, 8. And here are chlorines, this one, the one on the right, 2, 4, 6, 8. Yep, they each have 8. So therefore, they are sharing those electrons. Note that we can draw a line between two atoms to show the sharing of two electrons. You don't have to draw a line. Sometimes you could just leave them as two dots. But a line indicates shared electrons. Now, what if the two atoms that are sharing electrons do not have the same electronegativity? That would mean that they're sharing unevenly. And that would be a polar covalent bond, not nonpolar. And again, it's if the two atoms have a difference in electronegativity, then the bond is polar. And keep in mind that we're saying as long as they're not ionic, because obviously Na and Cl have different electronegativities, but that's not covalent, that's ionic, that's extreme. That is not even in the covalent category. So we're talking about where they're sharing electrons unevenly by having different electronegativities, but not so big a difference that it becomes ionic. So let me give you an example of that. Let's look at HCl. So here's H. H has one valence electron. Here is Cl. Cl has 7. They're going to share these two electrons, and they're going to make a bond, so it's going to look like this, HCl. Now, that is clearly a covalent bond. They're sharing those two. But are they sharing evenly? No, because remember, chlorine had a 3.2 for electronegativity, and hydrogen had only a 2.2, which means the electrons are being shared, but they're being pulled in that direction, which makes it polar. All right? Also note that hydrogen does not have an octet of electrons. It only has 2 electrons around it. But that's okay because remember hydrogen is such a small atom that on the first level you can only have 2 electrons anyway. So for hydrogen this is like an octet. I realize it's not 8, but it serves the purpose. So now what I want to talk about is something called multiple bonds. Now multiple bonds is exactly what it sounds like. It's when you have more than a single bond. So let's look at the compound CO2, and remember that C has 4 valence electrons and O has 6, and I drew these 4 really big because I want to make a distinction between these 4 and these 6. So I realized that CO2 is going to have 1 C and 2 O's, so I started to draw CO2 like this. There are C's 4, and there are oxygens 8, and there are oxygens 8. So if I try to make a bond here and a bond here, let me count how many dots are now around the O's and the C's. This O has 1, 2, 3, 4, 5, 6, and 7 because it's sharing. That's not enough. Same with this O, 1, 2, 3, 4, 5, 6, 7. And even the carbon has only 1, 2, 3, 4, 5, and 6. None of them have an octet, which means this is wrong. It couldn't possibly look like this. But here's what I could do. What if I were to take this electron and move it to the middle, this electron and move it to the middle, this electron and move it to the middle, and this electron and move it to the middle. Well, then what I would have is 2 sets of double bonds, a double bond here and a double bond here. So let's see if that will work with the octet rule. Now this oxygen has 1, 2, 3, 4, 5, 6, 7, 8. I'll draw a line there and there. Yeah, that oxygen is happy. And the same with this one, 1, 2, 3, 4, 5, 6, 7, 8. So it has bonds there and there. This oxygen is happy. And what about the carbon in the center? 1, 2, 3, 4, 5, 6, 7, 8. Yep, they all have their octet. So that means this is how you draw CO2. It's 2 double bonds. Let me show you another example of a double bond. O2. So again, here's O2. Remember, O has 6 dots. I'm not going to count them. You can count for yourself. So if I try to make a single bond between the 2 O's, I have 1, 2, 3, 4, 5, 6, 7 for both of them. No good. They need to have 8. So remember, when a single bond didn't work, what do we try? Let's try moving an electron from the bottom to the middle and also from the bottom to the middle and make a double bond. Now, there's a double bond between these two. And if you count, 2, 4, 6, 8, 2, 4, 6, 8. Yep, they both have 8, so it works. Can we go bigger than double? Can we go beyond sharing 2 sets or 4 electrons? Well, I'm not going to draw the before picture. I'm just going to show you what nitrogen looks like when it's done. Remember, nitrogen has 5 valence electrons, so 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. And if they share these 6, now they have 2, 4, 6, 8. 2, 4, 6, 8, and nitrogen now works with a triple bond. Now, how did I know that nitrogen had a triple bond? I didn't. But if I started with single, I'd realize it wasn't enough, and if I try to make a double, it still wouldn't work. Only a triple will work for nitrogen. And in case you're wondering, is there such a thing as a quadruple bond? No, the maximum you can have between two atoms is 6 electrons. This brings us to a term called symmetry. You might have learned symmetry in math. Symmetry means it's even on all sides, or it's a mirror image. So if I have a picture that looks like this, and I cut it down the middle, it is symmetrical. So why am I talking about symmetry in bonding? Because let's go back to CO2. Now remember we said CO2 looks like this. It has a double bond here and a double bond here, and there are two different atoms attached to the carbon, one O and one O. Well, if I were to look up the electronegativities of C and O, clearly O has a higher electronegativity, which means these bonds are polar. They're being pulled in this direction. O is more negative. The same with between this C and this O. The bonds between the C and O are being pulled this way. So there are two polar bonds, or technically 4 polar bonds, these two and these two. But here's the thing about carbon dioxide. It is still a non-polar molecule. Well, how can that be? I just said it had 4 polar bonds. Well, it's a non-polar molecule with polar bonds, because whenever there's a molecule that's symmetrical, it's not that there is no pull. There is a pull. There's a pull here and a pull here. But would you agree that these pulls are equal? Well, if the pulls cancel, even though the bonds are polar, the molecule is symmetrical, therefore it is non-polar. Here's another example of a molecule that has polar bonds. Methane is CH4. It's a carbon with 4 hydrogens. I've already drawn it out for you. You can see how it works. And again, the bond between C and H, that's got to be polar. Same with this one, same with this one, same with this one. But it has 4 polar bonds, and every bond cancels out every other bond. The pull this way is canceled by the pull this way. The pull this way is canceled by the pull this way. So once again, it's a non-polar molecule, even though it has polar bonds. Now let me show you one that is not symmetrical, or what's called asymmetrical. Ammonia has the formula NH3. So when I draw it out, here's the N. It has 5 dots, 1, 2, 3, 4, 5. And this time I drew little X's for the hydrogens so that they don't get confused with the nitrogen's electrons. And when I put it together, now the nitrogen has its 8, its octet, 2, 4, 6, 8, and the hydrogen has its 2, so it's happy. But ammonia, NH3, is not symmetrical. There's a pull here, there's a pull here, so those two cancel. There's a pull down, but there's no pull up. There's only a pair of electrons here, which means it's asymmetrical, so this is a polar molecule, which is what you'd expect anyway. There were polar bonds in there. Let me show you a couple more. Here is water. Now, it depends on how you draw water. I'm going to tell you right now that this is how water is drawn. It's not a straight line like this. It's going down and down. It's bent. Now, I realize we don't understand why it's bent yet. We'll learn that at a later lesson. But because it is bent, that means there's a pull between the H and the O this way, a pull between the H and the O this way, but there's no pull in these two directions. There's nothing here, there's nothing here, which means it's still polar. The pulls down are not, there's no pull up to cancel it. So it's non-symmetrical or asymmetrical, which means it's polar. Water is very polar. The last example I want to give you is something called coordinate covalent. Now, what does coordinate covalent mean? Coordinate covalent means you have covalent bonds, but this time at least 2 of the electrons are coming from the same atom. It's another way of saying, look, I'm sharing electrons with you, but I'm the one doing all the sharing. You're just tagging along for the ride. It may not seem fair, but it does happen. So there is a polyatomic ion on table E which is called ammonium. It sounds a lot like ammonia, but it's an ion called ammonium. So first let's take a look at NH3. We've already seen NH3 before. It looks like this. Now let's say there's a hydrogen ion, an H+, a hydrogen that's lost one of its electrons and wants to jump on board right here. Well, it can, because there are 2 electrons here, and that's exactly what H+ needs. So when I'm done, I've made NH4 with a +1 charge. So are these electrons right here being shared? Sure they are. But is hydrogen actually donating anything to the center? No, hydrogen's just joining, and nitrogen's being awfully generous. So is it covalent? Absolutely. But since nitrogen's doing all the work, we call it coordinate covalent. So to make it very easy, what I found is anytime you have a polyatomic ion, it is usually going to be coordinate covalent because of something like this is going to happen. And the way you draw it is draw the NH4 and then you put brackets around it and put a plus on the outside showing that, you know what, this actually has a charge.